I would like to start by asking you guys to imagine like what kind of abilities you would want from your personal assistant to have in general. So I myself actually tried to list some of those. So obviously, like driving me to work would be wonderful. Even better, making my presentations. I guess all of us would love that. And things like more realistic stuff like summarizing an NBA game, making a cup of coffee, and etc. So like among all of these, in my PhD, basically I worked on a few particular ones that are addressed by NLP research, which like examples of those are like booking a flight, making a restaurant reservation, answering questions, and etc. So obviously, like we don't want the rest to be ignored just because we don't work on them. Hopefully, they'll become real as well. But basically, like before kind of delving into more details of different tasks that I'll talk about today, I would like to like build some sort of a high-level framework, which I'll call as like bird's eye view of response generation in general. So basically, we would like to have an agent, and this agent will take some sort of request, and it will also have some sort of like world's knowledge. It could be, pretty much anything, in this picture. And I will have some, black box. I mean, like not quite black box, but it'll be kind of a black box that will actually help us generate the response for these incoming requests. And the examples of those really could be, again, summarizing an NBA game, answering questions, translating foreign news. So in my PhD, if you look at this picture, I focused on some parts of this black box, including model design, basically mostly like neural model design in my case, and also different learning schemes, including exploring different objectives that could be helpful for different tasks. Okay, so again, if you look at this picture, we see some variables in the high-level framework. One could be, for example, the knowledge, like what kind of knowledge we would want to be dealing with, and what kind of requests we can actually like really address. So starting with the knowledge, knowledge comes in kind of various forms, and most common types of knowledge that we use in NLP research are either like structured knowledge bases such as Freebase, or database tables, semi-structured web tables, or like completely unstructured text such as like product reviews, or Wikipedia article, or a news article. Excuse me. Okay, so going to the moving on to the requests, like what kind of tasks we would want to do with these knowledges. One like a good example that I have focused on in my PhD is question answering. So there are different types of question answering. Like it could be the examples here, or it could be some other examples such as like question answering from like exactly directly from text that I won't cover here. So these are good examples where like you have an incoming question such as like when did Shaq come into the NBA, and you would like to generate a precise answer to this question. And the answer in this case is going to be some entities which are like nodes in the knowledge graph. And on the other hand, if you want to kind of achieve a similar task on database tables, you could also have like a setting where you directly like pick cells of the knowledge base, but also at the same time you can try to generate the SQL query. So that's another focus that I worked on. So other than these, moving to more generative tasks, where like conversational response is one of them. So like a user is asking about Italian food in Los Altos, and the agent might say, okay, Pompeii is a nice restaurant in Los Altos serving Italian food. But at the same time, like the research in this area, like so far, showed us that this most of the time leads to assistants or whatever we call this agent that generate most of the time generic responses or like dull, uninformative responses. That is why the conversational response generation tasks that I focus use some sort of knowledge. We could call external knowledge. In this case, it could be like restaurant reviews, which you want to incorporate in the response generation, so that you have a chance to maybe like make it more interesting or more engaging for users. In which case, like you might want to include some specific information about the restaurant, maybe. Like that's basically like one use case. So summarization is, I think, another very interesting work or like very interesting task in general in NLP, where like you have input article which could be of length more than 1,000 tokens, and you would like to kind of summarize this into maybe just like a few sentences. So here the framework kind of changes a bit, but it's pretty much the request now is like static, just summarize this, and the knowledge becomes the article itself. So in general, like ultimate assistant at the end would be some agent that could actually like address multiple tasks that we might really want to use, basically by using different background knowledges, which actually are kind of in different structures. So this is, obviously, a very ambitious goal, and it's kind of like a long journey in which like many researchers will take part in. And I personally like worked on a few of these problems in my research. Just like quick overview. So I have worked, like my early works are in structured knowledge bases, which are mostly about question answering, basically like factoid question answering using freebase more specifically. And I also have like worked on semi-structured, like question answering on semi-structured tables, and more recently I have been working on response generation using unstructured knowledge. These are mostly like conditional text generation models in general. So in this talk, I will give you a brief overview of what I have done on structured knowledge bases, and then I will try to give you like a try to deliver you one of my recent works in more detail. So let's just start with with my work on structured knowledge bases, which I call factual response generation, because it's basically like there is some factual answer to your question that you're asking, and the agent needs to kind of retrieve that answer from the corresponding background knowledge. So basically in the general framework, it kind of looks like now the input is like a factoid question in natural language, and the knowledge is a huge knowledge base, which is free base, And you basically need a good model that kind of like can effectively represent both question and the knowledge base, and learn this model from the available training data, and by the end kind of try to answer your questions in the inference time. So as I said, I'll very briefly describe this work due to time limitation. So so the task basically kind of looks like this. Like you have a question, when did check come into the NBA, and in the middle you could use like a kind of different models. It could be like a neural model that can try to just like match the question to entities in the knowledge base, where the entities are represented like in any kind of any way that you want. But in general, like at the time that I worked on this problem, the state-of-the-art model was like a semantic parsing model from Stanford. And what I've done here is that I basically looked at kind of what alternative signals could be useful to improve this task. And more specifically, I looked at the answer type of the question. So if I was able to predict the answer type with 100% accuracy, how much would I be able to improve the state-of-the-art semantic parser on this task? And here the number you really want to look at is the first row, which is the performance of this semantic parser called agenda IL, which is like close to 50% in advanced score. And basically, and the last row, basically, if you assume that you know the answer type perfectly, then you could basically improve the result by like about 10% in advanced score. So this is kind of like the headroom that gives you the motivation to work on this. And briefly, the way that I kind of solved this task, I mean, the model that I proposed is consisting of 3 steps. The first step is kind of entity typing in context, where there is a question like when did check come into the NBA, and you're trying to basically abstract out this question by finding the right type of the shack, which is Shaquille O'Neal in this case, with the freebase types. And in the second component, you're trying to convert the question into declarative statement form, which is like which pretty much looks like subject relation object form. And the part in the middle is basically kind of clustering based approach. And finally, after applying these 2 transformations to the question, you try to find the answer type of the question. And the first and third kind of parts are like models that are trained on the data, and the one in the middle is basically like kind of obtained from the statistics of the training data. And here the data set we used is the web questions data from Stanford. And if you look at the results, so the first result I want to mention is the if we incorporate the type predictions that are outcome of our model and incorporate that onto agenda IL, then we can actually like improve the F1 score by about 3%. And there was a follow-up work that actually came out later than we did this work, which is from Scott Yee, called Stack. It's basically a neural semantic parser, and we also tried to apply our kind of model on top of his model. And then, although like it's a bit lower, we still see some improvements on the overall performance. So these are pretty much all the things I'll be able to say today about this work. Please let me know if you have any questions about this, probably later as well. So I'd like to move to the conversational response generation work that has recently appeared at the Conversational workshop at NeurIPS 2018. So just to set up like the context for this problem, basically now the input to the agent is the dialogue. It's like in general like the dialogue history, and we have some external knowledge that is relevant to the dialogue history, which you can kind of try to obtain offline in a way. And still we have like the black box and try to generate the response. And in this work, we basically are focusing on the model. We're basically going to propose a new model here that can address this problem. Actually, it will address the problem in a general way. So the particular like the particular task that we look at here is kind of use the external knowledge to make the conversation kind of more natural, engaging, and informative. That's sort of like the motivation of why we kind of try to incorporate the external knowledge. So the like previous work in this domain was like basically the ones that don't use the external knowledge. You basically train a model over only the dialogues, right? So basically, you take the dialogue history, and then the model is trying to generate the next, utterance in the next turn. And here, if you think about it, modeling the open dialogue in this way is a little bit difficult because you just need to encode kind of the knowledge in the model parameters, right? So that's like you don't have any alternative. So which means like you need like tons of data to kind of cover all kinds of knowledge. And like maybe minor, but another downside is just like it would need retraining as the new knowledge becomes available. So recently there was a work called a knowledge grounded neural conversation model, which tried to kind of propose like a new kind of setup. It's kind of a new setup for the dialogue research, where they propose that instead of like trying to encode everything in the model parameters, like basically use the external knowledge as an input, which actually what humans do as well. Like that's why we kind of I think discovered kind of writing. So and before like going into details of other things that I will talk about this work, I would like to just give you a spoiler about the end. And basically at the end, this is the model I'm going to try to convince you guys that that's a good model for this task. So basically we call it DEEPCOPY. And so what it basically does is that you have the dialogue context, which is the dialogue history. This is one of the inputs to your model. And the other input is basically knowledge source, which you could think of it as like a kind of set of text pieces, like set of sentences. We will call them facts. So this model basically what it does is at every and obviously we have a decoder that tries to generate the required or like actually desired response. And this model is basically going to generate every token of this response once at a time. And at every decoding step, it will have attention to dialogue context and the knowledge source. Based on this, like it will have like a fixed generation probability, fixed generation vocabulary over which it will compute a distribution. But on top of all these, we will also try to equip this model with like a hierarchical copy mechanism where you can actually like copy tokens from the dialogue context, and at the same time you can copy stuff from the knowledge source. And so basically you have two soft switches here, like basically two soft gates, where you try to decide whether at this time step whether you want to generate a word or whether you want to copy some word from the input that you have. And if you want to copy, which source do you want to pick? Like, do you want to copy from the dialog context, or do you want to copy from the knowledge source? And for each of those, we will induce a probability distribution based on the attention, and then at the end, we'll combine all these like output probability distributions to induce one single probability distribution over which we will train the model. Okay, so basically, if you think about that model that I've described, it's kind of even like a more general model that can be applied to, other question answering tasks. It's just not for this, only for this dialogue task. If you think about, like, you have a question and then you have a bunch of knowledges, it could also be like coming from different domains. You can kind of add another hierarchy there, and you can try to generate like the answer for your question. So it's basically like a general model. And then we obviously like compared this with all the existing works in this domain, and on top of that, we propose additional kind of natural baselines ourselves. And finally, like, we compare everything with the DEEPCOPY. Okay, so the data set that we actually like looked at two data sets for this task, but I'll cover one of them, which is like more fun to talk about. So this is a Convey-2 data set released by Facebook last year, and the way that it is obtained is basically you have like two persons talk to each other based on the persona that they're given. And so one training example here would be like you have a dialog context, just to exemplify, and then you have a response that you want to generate. So there is like some challenges in this data set. Like, one is being able to incorporate the factual stuff in the persona into the responses. Like, for example, the Game of Thrones here is just like not going to make it to the vocabulary because of the sparsity. I mean, that's how we can actually incorporate that into response generation. I mean, that's where the copy stuff will come in. And another thing is that obviously, like, due to high entropy of open domain dialogues between two persons, not all the facts, like not all the possibilities can be covered by these facts that the persons are provided. That's why they make up some facts. I call them like hallucinated facts, where it's pretty difficult for model to kind of recover those. And finally, there's like all kinds of humor that's also like kind of difficult to recover by the models. Okay, so just to tell you a little bit about evaluation metrics, we have like all different kinds of automated metrics, which are used commonly for text generation tasks. Perplexity, Blue, Rugel, Cider. And for human evaluation, we also do human evaluation on the generated responses, where we look at the fact inclusion, which is like, does the response include a fact? So this could be like a kind of any fact, like a hallucinated fact would be counted as a fact for this metric. And then you have factual correctness, which is like whether the included fact is a correct one, like whether it is within your persona. And coherence is basically if there is some sort of like this is a little bit ambiguous metric, but the thing that we try to capture here is whether the responses that you generate are kind of like related to the overall persona that you have, although it doesn't like specifically kind of use one fact from it. And finally, we have like independent of the facts, the naturalness score, which kind of tries to judge whether the generated response in general is good or not. And this is like a rating from 1 to 5. So quickly, I'll go over the models, like first the baseline models and then the proposed models. So the seek-to-seek with attention is like a natural baseline where we don't use the facts. This is just to kind of isolate the effects of using facts in recovering the correct response. So basically, it's like a sequence-to-sequence model with attention, and the only input to the model is the dialog context. And we also have a seek-to-seek with single fact. So single fact here is like you have a bunch of facts in your persona, and what we try to achieve here is like what happens if we select one of them which we think kind of is the most relevant one, and then append it to the input and just run the seek-to-seek model as it was. And here the question is, how do you pick the fact? So we have like two ways. One is like best fact context, so which is basically like you look at the dialog context and try to identify the most similar fact based on its TF-IDF score with the context. And we also have best fact response, which is a cheating model to understand like what you would be able to do if you were given almost the correct fact for that turn. So which is obtained by TF-IDF similarity of facts to the ground truth response, basically. So if we look at the results for the baselines that I've described so far. So like, you know, we have like no fact, best fact context, and best fact response. And here, like we can see that you know, on the perplexity, the results are as expected. Also, like for you know, factual evaluations, you know, if you use a relevant fact, it improves. But if you use kind of almost the best fact, then it improves more. But for the naturalness, it's like somehow dropping a bit, although not much. But the reason, like I've actually looked into the, you know, examples that are evaluated, and the common like reason why the scores are lower is because the no fact one basically generates generic responses such as like you know, what do you do for work, and then that is rated higher than the response that tries to include a fact but kind of fails in the grammar a little bit. Okay, so now what we will do is that, so now we have a sequence-to-sequence model with attention, and then we will use an existing model, which is like kind of proposed in 2017. Basically, it just adds like a copy mechanism on top of the sequence-to-sequence model. So basically here what we will do is that on the previous three models that I've described, we just add this component that tries to copy from the input sequence. So basically, if you add, like the input just is the same, you just add the copy mechanism on top of this, and you can immediately see like everything kind of gets better, like you know, even like including the naturalness. So this is basically just like saying, okay, copy hubs for this task. Okay, so most of the existing works that I'm aware of in this, like for this task, a kind of uses memory networks, and I'll briefly describe how they're used. So now let's say like we have the facts, and we have like a fact encoder, which is like key value memory network, where you have like a key representation for each fact and value representation for each fact. And then you have like a context encoder, which is usually like a sequence model, like an LSTM. And then you kind of take the last, you know, last hidden state of this LSTM, and then do attention on the key representations of the facts. And then based on the, you know, attention weights, you compute, you know, summary of the fact representation as the weighted average of the, you know, value representations using the attention weights. And then you take this single representation of the facts and then kind of add it to the context representation and just decode from that. So this is like the model that is used in the, okay, so that's just, I mean, we will basically call that component a memory network. And this exact model is used in the initial work called a knowledge-grounded neural conversation model. So we will call this a memory network, and just to recall when we compare the results. And then we also like here, like these are like kind of, in my opinion, natural extensions to the memory network model I've just described, where basically in the decoder, you also add like attention, kind of enable attention mechanism on the context, or or facts, right? So basically, like in the decoder, you could still look back, right? Why not? And actually, you can kind of do both as well, like look back on both facts and context. Why not? So basically, those are like the last three memory network models are just like out of curiosity. We want to look into them as well. So if we compare the results here, so I mean one of the observations is that attention over facts only results in a bad fact incorporation. And I think more importantly, like even when you do memnet in the decoder, if you look back on both fact and context by attention, you do better basically. And I think that's like a natural result. But another like observation here is that best fact context plus copy, which is the baseline that we proposed at the beginning, it kind of does. I mean, I would say much better than the memnet-based models. So, so these are like some observations. So now I would like to move on to a model called multi-seek-to-seek that we explore as kind of like the preliminary version of the DEEPCOPY. So the idea here is basically, can we condition the response on a few facts or fact tokens instead of like having a single fact representation? And in the follow-up like extension of this, which we will call DEEPCOPY, and we'll look at can we copy tokens from both the dialog history and the facts. So in this one, basically, what we do is that we encode the facts with a sequence model as well. So that basically results in like hidden vectors at for pretty much like every token of the fact. And then what we do is that in the decoder, we attend on these token representation first, which will give us like a attention distribution over the tokens of every fact. And then we compute the fact context vectors, which are like the weighted sum of the token representations, kind of weighted by the attention weights. And then we do we add another attention layer on the fact representations. And then this gives like basically gives us a distribution over the facts. And then we also have like a attention on the context, context encodings. So we basically combine all this into one single fact representation and also one single context representation, and then use these two together with the decoder state to output a word at every time step from a fixed vocabulary. So this is kind of just like instead of using memnet for fact encoding, what happens if you use LSTM plus hierarchical attention on top of that. I mean, this basically kind of enables you to, attend to different fact tokens at each decoder step.
Are you getting largely grammatical sentences out?
You mean for this model?
Yeah.
Yes, I don't think by the end of the day, this model is not going to perform good, but I'm not quite sure if it's due to grammar. Yes, but this model doesn't perform good. So basically now, on top of this model, we would like to add the copy mechanism, which will basically there's two advantages of the copy mechanism. One is like kind of reproducing stuff like Game of Thrones, obviously, and another I think like implicit benefit of the copy mechanism is you kind of in a way do indirect attention supervision, because like if this token appears in your input or like your facts, then you directly the attention distribution goes to the output distribution. In this way, you basically add like an immediate gradient link to the attention. So, I mean, basically, the deep copy by the end of the day is just you have that multi-sig-to-sig model, which actually gives you like a kind of distribution over the fact tokens, distribution over the context tokens, and then distribution over the individual facts. So basically, you can take the distribution over the facts together with the distribution over, fact tokens and the facts. You can basically induce, one single distribution for every unique token in your facts, right? And then similarly for the context tokens. Sorry. And then basically what you need now is you need basically two soft gates that will give you the decisions on how you will combine all of these at the end. And basically that is defined by like a a feed-forward layer using the context vectors followed by a sigmoid layer.
Question?
Sure.
How many facts does it have to attend to at every time?
So that's a good question. In this data set, it's at most 5 for this data set. But if it is, we also worked on another data set where it could go up to like thousands, for which you need to do some other stuff because it's not much scalable. If that's what your question. Yeah. So I mean for that you need to do like some offline pre-processing of the facts. And yeah, so this is like the final picture I just described at the beginning. If you have any questions about this, please ask me. So if we look at the results, so basically like DEEPCOPY performs much better on the automated metrics, which I included here, like a perplexity and blue, and it's kind of the case for the other automated metrics as well. But on the fact evaluation, we can see that DEEPCOPY actually can kind of can do a little bit inferior to the best fact context plus copy, which is like one of the baselines that we proposed, especially on like if you look at the fact inclusion and fact correctness columns. So here one observation is that since best fact context plus copy kind of brings more facts because like it's 66% to 54%, that might be the reason why it gets like more correct ones. That's why we also like kind of wanted to look at like the precision, fact precision, which is like basically how many of the times that you bring a fact in your response you're correct, right? And if you look at this table, then I mean it's still a bit worse, but I don't think it's like that much different. So in general, like we can kind of conclude that DEEPCOPY could be more preferred model over the other ones for this task.
So for factual precision, you said that's when the system provides a response that's correct. It's including a fact which is correct.
Including a fact. So basically, over all the responses that you include a fact, how many of what is the percentage of times you include a correct fact?
Oh, I see. Okay. Well, what percentage of responses actually require a fact?
That's a good one. If you look at the ground truth down there, it's 64%, which is like it's not 100% because of the hallucinated facts mostly.
Okay.
What do you mean by?
Sorry, go ahead.
What do you mean by including the fact? I thought you always include the representation of the facts. Several of these problems.
Oh, I mean, I actually mean like including the actual fact, like the words, not the model. Like I'm talking about the results. Like let's say the model generated some response, right? Whether it actually includes any fact in terms of like any factual information, such as like I have 3 children from age 10 to 21. This is a fact, but if it's not in your persona, then it's a hallucinated fact.
And what degree of copying a fact counts as inclusion? So do you have to copy just one word from a remembered fact, or all of the words, or?
Oh, I see. Like you mean in order to count the fact as a correct?
Right. I mean, suppose the persona says I have a big brown cat, and the response is I have a cat. Is that including the facts or not?
It actually does not.
Okay,
Yeah.
so it's got to include everything.
Yeah, pretty much. Like I mean, it's a little bit ambiguous, obviously, but like the way that we instruct the human evaluators is to basically include, like if you're using a fact, just include include all the subjective information there, basically.
So this is human evaluation.
Yeah.
of this fact, okay.
So this is basically like human evaluation over like three humans. And I also looked at like some diversity results, like basically you look at the, all the generated responses and then count different n-grams and compare them to the, n-grams appearing in the ground truth responses. So there we also like see that, DEEPCOPY can kind of generate, more diverse responses. And just like one example to give you a bit, a more clear idea, maybe. So basically, on the right we have the, person 1, person 2. These are like the last 2 turns, and then we want the person 1 to kind of generate a response now, for which we use our models, and the persona facts on the left are corresponding to person 1's persona facts, and basically, like if you look at the dialogue. I couldn't include the previous turns, but here basically person 2 is saying like, oh my god, I'm glad you did. Do you work now? Like person 1 had like some health issue in the past, and then MemNet model says, yes, I do not work, but I do not work, and these are like the best. Like this is the best MemNet model response, and then best sequence to sequence model response is no, I have a job at a restaurant. And the best sequence to sequence plus copy model, which is actually the cheating model that uses the correct fact pretty much. And it says I'm a life coach, and DEEPCOPY says yes, I just got a new job. So here I just want to make the distinction that the sequence to sequence double star again just uses the correct fact, but DEEPCOPY is just given all the facts. It just needs to figure out which fact it needs to use. And, sure.
Which part of the network or which part of the system is encouraging diversity?
So there's actually not like explicit, component or like, constraint that encourages diversity. But basically, you train all the models on the same training data, right? And and being able to copy, as we see in the other models as well, which uses the copy, but not the hierarchical copy. Copy helps, right? Because you can bring in stuff that's not in your vocabulary, right? Like you can copy so that now you have a new n-gram, which you wouldn't be able to have the otherwise, right? That's one way, and another one, I guess, like why DEEPCOPY does better. Maybe because like you can kind of like copy tokens from different facts. But this is just hypothesis. I haven't looked into it really. Yeah.
Sorry, one quick question. Are your responses always in response to a question? You're assuming that the person who's asked a question rather than made a statement. Do you consider responses to statements that a person may have made?
Well, I mean, not always. It's basically sometimes, in this example, yes, but maybe in some examples it could be person 1 is starting a different conversation, like kind of based on like using one of the facts. Maybe that's not used before. It just says, okay, I like playing football. How about you? something like that. That could also be the case.
Your system might respond with a question, though.
It could respond with a question as well. Yes, it could respond with a question as well. Like it could sometimes, like for example, the guy asks what do you do for work? It says something and then asks, what about you? It could also like directly ask a question as well. Yeah, I mean there's such cases because those are existing in the training data, right? And like regarding what the DEEPCOPY does, it can actually kind of attend on the right personal fact, and on top of that, it can copy kind of really exactly the relevant pieces instead of like it could really just copy the entire fact as well, right? In which case it doesn't. It just starts with like answering the question, saying yes, and then going on with I just got a new job, which is kind of a mixture of like copying and generating modes. Just like a few takeaways. We propose the general model here for kind of conditional text generation, where like the conditioning is on. Maybe like we could consider it as like one query plus some hierarchical external knowledge. And then we've shown that it might like it's at least for this task, for this data set, and actually another data set which is called like the SDC 7 track 2. It is like basically superior to the baseline models. Finally, it basically yields to more diverse responses. I would like to just talk a little bit about the feature work. So currently, like I'm interested in again response generation, but in kind of more task-oriented setting, which I would say might be more useful, for some like real application scenarios. So basically, like what we want is that we want to have like end-to-end neural model which could use like structured knowledge together with unstructured knowledge for task-oriented dialogues. I mean here we don't really have, for this data set at least, we don't really have the unstructured knowledge part. But so this time, instead of like having unstructured knowledge for this task as the external knowledge, how you can have like an end-to-end model that can actually use the structured knowledge, which is like the knowledge base or like database in this case. And basically this model should be able to do database lookup together with response generation. How can we build this model? That's one of the things I'm looking at. And like in general, this model leads to generate kind of dialogue acts and also generate the natural language response. So and this, there is like a good data set that's recently released, and we're looking into this. And the next one is kind of on top of one of my previous works that I wasn't able to talk about today. So it was about like conditional text generation, and just like to give you a little bit idea about what it looks like. So basically, this is like the way that we usually kind of generate the text, right? Like basically, we generate it token by token, and every time we generate a token, we input it to the next step and go on. And my previous work was basically looking into how can we build, how can we formulate a new objective function that would actually encourage, sequence level training. And in this like feature work, what I am looking at is how can we design edit-based decoders, which is basically which is going to be able to revisit prefix prefix hypothesis, which means like can you edit whatever you have already generated. Like in general, I believe like the kind of motivation here is that like as a human, even when we write something, like we kind of go back and modify we wrote before, and if you want to generate a long text, this might be like kind of one way to go. And another immediate benefit of this would be like kind of it could provide more flexibility for streaming NLP applications, such as machine translation. Yes, so with that, I would like to finish my talk, and I'll be happy to take any questions.